Hey guys, in this video we're going to talk about Chapter 9, Section 5, Power Series and Interval of Convergence. So the first thing that you should ask yourself is, what is a power series? Well, this is the definition. So a power series is a series with a variable x or some other variable in it, and it's centered at the point we call the center at the point x equals a. It's a sum of constants times powers of x minus a. And so it's of this form right here, where when you expand it, you get a sub 0 plus a sub 1 times x minus a plus a sub 2 times x minus a squared, and a is just going to be some number, wherever this power series is centered. So that is the definition. Before we get into talking about whether power series converge or diverge, I want to first do some practice finding the center of the power series, because the center is going to be relevant to us in terms of where a power series converges or diverges. So let's do some practice with this. So remember that this guy, this a sub n, is going to be our n terms, and this x minus a is going to, we want to set that thing equal to 0 to find the center. So maybe I'll write a note of this here. So want to set x minus a equal to 0 and solve for x to find the center. Okay, so let's go ahead and do that with this problem. So this is the a sub n part, because it doesn't involve any x's. So this guy is what we're going to set equal to 0, because 2 is acting like our a in this case. So x minus 2 is equal to 0, and therefore our center is at x equals 2. So that's our answer here. That is our center. What about the next one? So this guy is our a sub n term, because it doesn't involve the variable x. So what we're going to set equal to 0 is this guy, x plus 4. So when x plus 4 equals 0, we get that x is equal to negative 4. So this guy is our center. Let's do some more examples. All right, so you want to identify what is your a sub n and what is your x minus a to the n term. Well, our a sub n isn't going to involve the variable x, so it's going to be all of this. This is our a sub n. And then the rest of it is going to be our x minus a to the n. Now notice that we don't have an a that we can see, but we can rewrite this guy as x minus 0 to the n, right? And if we set that equal to 0, well then, of course, we see that our center is going to be 0. Okay? All right, so let's see. In this case, our a sub n is going to be 1 over n plus 1 factorial. And then our x minus a to some power, it can be n or it can be n plus 1, whatever, is going to be this top term. So we want to set basically everything in the parentheses equal to 0 and solve for x. So x is equal to pi over 2. So this is our center in this case. Our definition there. So I just want to make a point right here, and the point I'll get to as soon as we do these first two problems. It says determine whether the power series converges or diverges for x equals negative 1 and x equals 3. So before, when we were trying to figure out whether a series converged or diverged, it was just, they either converge or diverge, right? We didn't have any kind of we didn't have any changing variables like we do with power series. So if I plug in negative 1 in for x into this series, what I'm going to get here is the following. I have n equals 0 to infinity, and instead of x, I'm putting negative 1 to the n all over 2 to the n. So if we were to expand this out, when n equals 0, we get 1 on top and 1 on bottom, so that's simply 1. Plus, when n equals 1, we're just going up. When n equals 1, we get negative 1 over 2. When n equals 2, we get 1 over 4, etc. So this is an alternating series. And in particular, it's an alternating geometric series. So what is the common ratio here to get from one term to the next? Well, it's going to be negative 1/2, right? If I multiply negative 1/2 by each term, I get the next term. So my common ratio is negative 1/2, and we know whether a geometric series converges or diverges strictly by the common ratio. So remember, if the common ratio, which in our case is negative 1/2, is less than 1, if the absolute value of negative 1/2 is less than 1, then this thing is going to converge. And indeed it does, because the absolute value of negative 1/2 is 1/2, which is 1, and therefore this converges, this power series converges for x equals negative 1. All right. Now let's take a look at what happens when x equals 3 with this power series. If we plug in 3 this time for x, we're going to get the series from n equals 0 to infinity, just regular 3 to the n over 2 to the n. And again, this is a geometric series. When n equals 0, we get 1. When n equals 1, we get 3/2. When n equals 2, we get 9/4, and so forth. So the common ratio here is 3/2, right? Now the absolute value of 3/2 is greater than 1. And remember, when that happened, the geometric series diverges. And so we have diverges for x is equal to 3. So what's the point that I'm trying to make with this example? Let's write it down. The point is this. A power series can converge or diverge depending on x, depending what our x is. So for these things, x is going to be fixed. You pick a number, you plug it in, and you see what happens there. And that's the point I'm trying to make here. So what we're going to do next is we're going to use the ratio test from last week to see precisely when these power series will converge or diverge. For which x values will that happen? That's what we're interested in. And later on, we're going to talk about how we can actually represent functions with power series, and then, what we're learning now is going to play into what the domain of these functions are. So let's go right ahead and talk about this first example. So the big idea here, this is a big point, is that the power series is going to converge for certain values of x, and it's going to diverge for certain values of x. Sometimes it converges for all x. Sometimes it only converges for one specific x. And that's what we're going to look at. So let's take a look at this example. It says, for which values of x does this series converge for, and which values of x does it diverge for? So we can see here that this sum is just a geometric series. Let's investigate. let's expand it out and see why it's geometric. So this is a power series, right? Because we have a variable x raised to a power n. And when I expand this thing, what I'm going to get is x to the 0 first, and that's 1, plus x to the 1, x to the 2, which is x squared, and so forth. So the key idea here is I mean, it's not the key idea, but it's one idea. This is geometric. What's the common ratio? What's the common ratio? The common ratio, what do I have to multiply each term to get the next one by? I have to multiply by x, right? So the common ratio is going to be x. And what we know about geometric series is the following, is that when the absolute value of that common ratio, which in this specific case is x, when that absolute value is less than 1, this thing is going to converge. And when the absolute value of this thing is greater than 1, it's going to diverge. So that's it. So that was the answer to the question. Now we can write these things a little bit more, like, to look a little bit more familiar, I suppose. If we want to get rid of the absolute value bar, and actually I'm just gonna keep this converging thing, and then we'll talk about the divergence in a second. But when we get rid of the absolute value bar, we have two options, right? Because whenever we put something in the absolute value bars, it's always going to be positive when we take them away, right? When we evaluate the absolute value of something. So we have two options here, what's in the absolute value bar. We either have that thing's positive, x is less than 1, or the other option is that it ended up being negative, right? The inside is negative. So we either have x is less than 1 or negative x is less than 1. We divide both sides by negative 1. We flip the sign over here and we get x is greater than negative 1. So if we write this, in terms of intervals, we have that x is greater than negative 1 and x is less than 1. So this power series converges for x is bigger than negative 1 and less than 1. So this is our answer here. And it diverges otherwise. Okay. All right. So we are going to be using the ratio test quite a bit in this video. So just remind yourself of what this is from last week. We're gonna check to see where these series converge with the ratio test. And this is it if you forgot it. So basically, we take the limit of the function subbing in n plus 1 in for the numerator, and then we're going to divide that by just the regular sequence, a sub n. We're going to get some kind of limit. If the limit is less than 1, we know that the series converges. If it's greater than 1, the series diverges. And if it's equal 1, we can't determine convergence or divergence. Okay? So let's look at an example here where we're going to use the ratio test to see for which values of x does this thing converge. Okay. So what we're going to do is we're going to take the limit as n goes to infinity. And this is like, we can think of this as our a sub n. And so a sub n plus 1, we're just subbing in n plus 1 anywhere we see an n into that. So we have the absolute value of n plus 1 factorial times x to the n plus 1, all divided by a sub n, which is just n factorial x to the n. So again, I'm just subbing in, this top is a sub n plus 1, and the bottom is just a sub n. All right? So, and notice that I put the whole thing in the absolute value bars, which you can do. I mean, in the book, it's going to give you the top in absolute value bars divided by the bottom in absolute value bars, but you can also write it like this. So let's go ahead and figure out what the heck this is. Now, I can simplify. I don't want to do anything with the absolute value bars quite yet, but what I can do on the inside is I can simplify this because first of all, let's look at this factorial business. What does factorial mean? Well, some people, I think of it like this. I think of, if we have 4 factorial, we're starting at 1 times 2 times 3 times all the way till we get to 4, right? So 4 plus 1 factorial is just going to be 1 times 2 times 3 times 4 times the number after 4, which is 5. All right? So that's the idea here is on top, this n plus 1 factorial is going to be 1 times 2 times ... times all the way to n plus 1, whatever that is. Well, actually, let's write it like this. Times n plus 1, all right? Over n factorial is just 1 times 2 times all the way up till n. And then we still have this other business. We have x to the n plus 1 on top and x to the n on bottom. Now what's awesome here is this guy cancels with this guy, and I'm simply left with n plus 1 on top. And what happens with this business? Well, I can just use this property of exponents that says when I divide exponential expressions with the same base, I keep the base and I subtract top exponent minus bottom exponent. Okay, this is the property of exponents that you guys should be familiar with. So when I do that, n minus n, I just get 1 in the exponent. So this whole thing that I circled just becomes x to the first, right? All right, so let's rewrite this. Limit n goes to infinity of n plus 1 on top. Then we just found out that this was times x. I'm going to keep this n plus 1 in parentheses just to be careful, all right? Now, what I can do, okay, you want to be careful with these absolute value bars because they do matter sometimes. Now, they don't matter in the case of n because n is always going to be positive, right? We start at n equals 0 and we're going up to infinity, right? So we can take the n plus 1, we can always take n's out of the absolute value bar, but we cannot take the x out of the absolute value bar. Why is that? Why is that? Well, because the absolute value of x does not necessarily equal x, right? What if x is negative 1? Well, the absolute value of negative 1 is positive 1. Those don't equal each other, right? So that's why we can't divorce the absolute value bars from x, okay? But we can take them off of the n plus 1. So what I'm going to do is I'm going to bring out this absolute value of x in the front, and now I'm just left with the limit as n goes to infinity of n plus 1. Okay. Now, when n goes to infinity, of course, this thing goes to infinity, right? Infinity plus 1 is infinity. And so I'm just left with the absolute value of x times infinity. So this is going to equal infinity for every value of x except one number. Can you guys think of the value of x that isn't going to make this infinity? Well, it's going to be 0, right? So this equals infinity for all x other than 0. All right? And it equals 0 when x equals 0. So we kind of have two cases here, right? So this, basically, these are going to be our L's, our limits for the ratio test. And remember what the ratio test says. The ratio test says if your L is greater than 0, it's divergent. Look at this. So this is going to be divergent for every x other than 0. But guess what, guys? This L is less than 1. So it's going to be convergent only for x equals 0. All right, so let's write that down. So what was it asking us? Let's see. For which values of x is it convergent? So therefore, let's make our conclusion here. Therefore, this is only convergent when x equals 0. Because if that's the case, the ratio test tells us that the limit L is 0. But the limit is infinity for all other x's, which is larger than 1. So the ratio test says, hey, the only x value that this is going to converge for is x equals 0. So that's our answer here. Okay, here's 3 different cases that you can have. We're going to talk about radius of convergence, and we're going to talk about the intervals of convergence. So case 1 is what we just did. Case 1 is when it only converges at the center. Now look at what we started with. Isn't the center of this thing 0? And we deduced that it only converges at x equals 0. So that's case 1. We already did that. Case 2 is that it converges for all values of x, right? So like, let's see, did we do an example with that? I believe we did. Oh, no, we didn't do one yet, but we're going to get to it. So case 2 is when it converges for all values of x. And we'll do an example like that in just a bit. Case 3 is if we have some kind of radius of convergence where, x converges, the power series converges for more than one value of x, but not infinitely many values of x. Well, actually, let's rephrase that. It's going it's going to be like a set bounded interval. Let's rephrase it like that. And I'm going to show you guys what I mean in a bit, but we already took care of case 1. We actually did case 3, right? Because case 3 was this guy. We said, yeah, it's going to converge when x is bigger than -1 and between 1, so it's like bounded between those two guys. So that's case 3, when it's bounded between two real numbers as opposed to just being like negative infinity to positive infinity. So we're going to do several examples of this. And the idea here, so these are some important ideas. The interval of convergence is always going to be at the center of the power series. It's going to be centered there. And the radius of convergence is the distance between the center and one of the endpoints. All right, so like let's do some examples with these ideas that we just learned, this new vocabulary. Okay, so we want to show that this power series is convergent for all x. So that means when we do the ratio test, what we should get is that all x is less than 1. Okay, so let's work on this. So again, for all of these, you're going to want to do your ratio test. And our ratio test says we're going to take the limit as n goes to infinity of the absolute value of, well, first I'm going to plug in n plus 1 anywhere I see an n. That's going to be my numerator. So I have, and actually so my numerator is going to be x to the n plus 1 over n plus 1 factorial. And then we're going to divide that by just the regular a sub n, which is going to be it's going to be x to the n over 1 over n factorial. So let's clean this up. Cleaning it up, I can change this complex fraction into multiplication by reciprocals. So I have keep the top fraction, which is this guy, multiplied by the bottom fraction flipped. So, and actually I shouldn't have wrote 1 over n factorial. I should have just wrote x to the n over n factorial. I apologize about that. Okay, so this is going to be times n factorial over x to the n, still in absolute value bars. Now, let's see what this is going to give us. When I do my exponent rule, I keep the base x, subtract the exponents. So n plus 1 minus n is simply going to be x to the first. Okay, so that turns into x. And then for this n factorial over n plus 1 factorial, we have times 1 times 2 all the way up times n divided by 1 times 2 times all the way up to n times n plus 1. So these guys are going to go away, and I'm just left with x over n plus 1. So limit as n goes to infinity, absolute value bars of x over n plus 1. So remember, I cannot divorce the absolute value bars with x, but I can with the n plus 1 because that's always positive. So I'm going to bring out the absolute value of x to the front, and I'm taking the limit as n goes to infinity of 1 over n plus 1. And we all know this goes to 0 when we plug in infinity. So what I'm left with is x times 0. Now, we can't plug in x equals infinity. I want to make that clear. X is going to be a fixed real number that we need to plug in here. And because that's the case, for any number we plug in for x, any number you can think of, our answer is always going to be 0, no matter what, right? So this is going to be equal to 0. And this, by the way, is our L from our ratio test. Now, what does the ratio test says? It says, hey, if that L is less than 1, this thing's going to converge. And because x can be whatever it wants, and it's always going to be convergent, it's always going to be 0, this thing is going to converge for all x values. So we can say that, therefore, the ratio test tells us this power series will converge for all x values. What does that mean in terms of like the radius and the interval? What does that mean? The interval of convergence is like where it can possibly converge. Well, if it can converge for all x values, then our interval of convergence is just negative infinity to positive infinity, right? Any value of x will converge. So that's our interval of convergence, where it can converge from negative infinity to positive infinity. And our radius of convergence, we usually call that capital R. So radius of convergence is going to be the distance from the center of the interval to the endpoint, which of course is infinity. I mean, what's the center of negative infinity to infinity? I mean, maybe you can think of it as 0, but the idea here is that that's going to be, that length is going to be infinite. So the radius of convergence in this case is r equals infinity. And those are going to be our answers here. Okay, let's do another example. So here we have a power series because I'm in the form x minus a. Now, right off the bat, I notice that my center is at 5, right? So that's important here. So let's go ahead and use the ratio test. Since I have this power series, I have a variable x raised to a power. So this is a power series. And I'm going to go ahead and do my ratio test. We're taking the limit as n goes to infinity of n plus 1 factorial times x minus 5 to the n plus 1. Right? I'm just plugging in n plus 1 anywhere I see an n in here in my formula. And then I'm going to divide that by just my regular formula, n factorial x minus 5 to the n. And I'm taking the absolute value. Okay, so let's clean it up here. I notice that I have the same base right here of x minus 5. So using my exponent rules, I can keep the base, which is x minus 5, and then subtract the top exponent minus the bottom exponent to just give me x minus 5 to the 1. All right, so this is limit as n goes to infinity of, this is x minus 5 to the 1. I'm not going to write the 1. And then, we've done problems like this with the n plus 1 factorial over n factorial. What is that going to turn into? Well, if you think about it, it's just going to turn into n plus 1, right? This is times n plus 1. And we've done lots of examples with that. So I'm not going to go ahead and expand it out. Okay, so here we are at this point in time. And the question is, what can I do? Well, remember, I can't divorce the absolute value bar from the x term. So I'm going to pull out this x minus 5 in the front. And I can pull out the n plus 1. Because, again, that n is going to be positive. And this clearly goes to infinity, right? So there's only one x value that we have trouble with, and that's when we have 0 times infinity, because then we'll have 0. So the x value that we have, so what we can say here, since this is infinite, by the ratio test, this power series doesn't converge except, what's the exception? Except when x equals 5. That's the exception. When x equals 5, this thing turns to 0, and this thing's going to converge to 0. But if x is anything else times infinity is infinity. So the ratio test concludes that the only point this thing converges at is at the center. And that's case 1, again, from our little list of cases. Right here, this previous problem was case 2. So this was case 2 from this. And here we have case 1. So how do I write the interval of convergence and the radius of convergence? Well, the interval of convergence is just going to be one single point at x equals 5. So our interval of convergence is just going to be the set containing 5. That's it. That's the only place it converges. And if you're just chilling on the number line at 5, if my only point is 5, what is the radius going to be? Like, how far does this thing reach out to include other things in convergence? Well, it doesn't, right? That's the only point that converges. So the radius, how far can we go and still be convergent, is 0. All right, so the radius of convergence is 0. So this is case 1. All right, let's do some more examples, guys. All right, let's look at this one. All right, so I encourage you to pause the video here, see if you can do this. Again, we're just using that ratio test to see what's going on here. And here we go. Limit as n goes to infinity of a sub n plus 1. I'm just plugging in n plus 1 wherever I see n's here. So I get x to the 2. And I'm going to be super careful here and make sure that in parentheses comes n plus 1 divided by 2 parentheses n plus 1 factorial, and this is in absolute value bars. Then I'm going to divide by just the regular formula that they give us, x to the 2n over 2n factorial. Okay, so far so good. This is a hot mess, but we can clean it up. Don't worry. So let's see what we can do here. Complex fraction. Keep the top fraction, multiply by the reciprocal of the bottom, and I'm going to do this I'm going to do this distribution right off the bat so that, I don't have to waste paper. Well, waste virtual paper, I guess. So on top, I have x to the 2n plus 2. Cool. Over, doing that distribution on bottom, I get 2n plus 2 factorial. All right, cool. And then this is where multiplication by the reciprocal comes from. So then I'm going to multiply by 2n factorial, all divided by x to the 2n. And this is in absolute value bars. Okay? So now I can clean this up. And this guy, right? I keep the base x, subtract the exponent, top minus bottom. 2n plus 2 minus 2n is simply 2. So I'm going to get x squared here. And then what's going to happen here? Well, if it helps you conceptualize this, you should do it. And I'm going to do it again here. This 2n factorial, what does that mean? Well, it means 1 times 2 times ... times all the way up to 2n. And on bottom, what does this 2n plus 2 factorial mean? Well, that means 1 times 2 times ... all the way to 2n times the next one. What's the next number? 2n plus 1 times the next one. What's the next one? 2n plus 2. And that's what that means. So what's amazing here is that this cancels and we're left with something a lot cleaner. So we have the limit as n goes to infinity of x squared on top. On bottom, we have 2n plus 1 times 2n plus 2. And at this point, everything can come out of the absolute value bars because x squared is always going to be positive. The absolute value of x squared, in other words, is always going to be equal to x squared. Okay? So that's why we can take it out. So, getting rid of those annoying bars, we have this. Now keep in mind that x is fixed, right? When we do these power series problems, we're plugging in, we're trying to see what happens when n goes to infinity, but x is a fixed number, right? So what happens when we plug in infinity into the bottom? Well, this whole thing's going to infinity, right? So we have some fixed number x squared over infinity. And what do we know about this? Well, we know that it goes to 0. For all x. There's no x value where this isn't going to equal 0, because remember, we can't plug in infinity for x. We're plugging in a fixed number, and infinity is not a fixed number. So this thing is always going to be 0. What does that tell us? Well, remember, what did we just find? We just used the ratio test to find an L, and this L is always going to be less than 1 for any value of x. What does that mean? That means that any x is fair game, right? That means that for any x, this thing is going to converge. This power series is going to converge. So what that tells us is that the radius of convergence is going to be infinity, because sky is the limit. X can be whatever it wants. And what is it asking us? Oh, the interval of convergence is, again, we're saying that x is going to be between negative infinity and positive infinity. So we could write it like this, or we could write it like negative infinity to positive infinity. It doesn't matter. But so this is the interval right here. And this is the radius of convergence. That's our answer here. Let's move forward. Godspeed. Okay, so now it just says determine the radius of convergence of this hot mess. Let's see if we can clean it up. So this dot is multiplication, by the way. I don't want, maybe I'll just make it a little bit bigger so it looks like an exclamation point, but it's not. Okay. So again, ratio test is our friend in this section. It works really nicely. So we're taking the limit as n goes to infinity, and first we're plugging in n plus 1 in for n, anywhere we see an n. So, and by the way, where is this thing centered? Where's this thing centered? Well, look at your x parenthesis term. It's centered at 1. That's where it's centered. So keep that in mind. Okay, so let's do this. So anywhere I see an n, I'm plugging in n plus 1 to the n plus 1. Cool. Okay, so that's my first part. My bottom part is just the regular function that they gave us, or the regular formula, however you want to classify that. Okay, so far so good. Now let's clean it up, because this is a mess. So I'm going to clean it up by doing my reciprocal trick. Okay, so I'm going to keep the top. And by the way, I'm going to simplify that to just n. So it's going to be x minus 1 to the n plus 1 over n plus 1 times 3 to the n plus 1. So that's just the a sub n plus 1 part. Now I'm going to multiply by the bottom flipped. So this is going to be n times 3 to the n over negative 1 to the n minus 1 times x minus 1 to the n. Okay, let's see if we can do any voodoo to make this look a little bit simpler. Well, Here's something we could do. Negative 1 to the n over negative 1 to the n minus 1 is going to be negative 1 to the n minus n minus 1, which is going to give us negative 1 to the 1, which is negative 1. Now, the absolute value of negative 1 is always going to be 1, so we can pull it out. Now, if we pull out 1, we can pretty much neglect it because it's multiplication by 1. So what I'm going to do is just get rid of those, okay? That cleans it up a little bit. Now I'm going to look at my x minus 1. So I have x minus 1 to the n plus 1. And then on the bottom, I have x minus 1 to the n. So I keep the base, x minus 1, and subtract top exponent minus bottom exponent to give me simply x minus 1. So that turns into just x minus 1. Okay, so this is just x minus 1. And then what about the n can't really do anything with the n plus 1 because they're not the same bases, so we kind of just have to leave those alone for a second. But what about 3 to the n over 3 to the n plus 1? Well, this time we have a common base of 3, so we have 3 to the n minus n plus 1, which gives us 3 to the minus 1 when we do that distribution, which is 1 over 3. Cool. All right. So we have the 1 over 3. And then we still have that n on top that I didn't deal with, and I still have the n plus 1 on bottom that I didn't deal with. But this is what we should look like at this step. Now, what I can do at this point is I can pull this out. The 1/3 can just come out of the absolute value altogether, but the x minus 1 has to stay in the absolute value because of what we talked about earlier in this video. So this is going to be this, and we still have limit, n goes to infinity, and I'm taking the n over n plus 1 out because that thing is positive. We don't need the absolute value bars. So what is this going to be when I take the limit as n goes to infinity? Well, I can do either L'Hopital's rule or divide top and bottom by the highest power term. L'Hopital's rule says that if I plug in infinity over infinity, I just get indeterminate form, and I can take the derivative of the top and the bottom. So by L'Hopital's rule, and again, you don't have to use L'Hopital's rule, this thing equals 1, right? Because derivative, let's do some scratch work over here. This is L'Hopital's. L'Hope. So when I take the derivative of n, that's going to be 1. When I take the derivative of n plus 1, well, that's also going to be 1. So 1 over 1 is 1, L'Hopital's rule. So by L'Hopital's rule, all we have left is 1/3 times absolute value of x minus 1 times 1, which I won't write. But where are we at here? Okay, so this is our limit, L, and we want to figure out where the original power series converges. So if this is equal to L, we're interested in when this is less than 1, right? That's what the ratio test tells us. It says, hey, when this thing is less than 1, your series is going to converge. All right, so let's see what happens when we set up that inequality. Okay, let's see. Okay, so what we have is, and maybe I'll just write a note of this, converges if L is less than 1. So this is what we have. We just found L. L was 1/3 absolute value of x minus 1. We want to see which x values make this converge. So this is the inequality we set up. What we can do to both sides first is multiply by 3. And we simply get, when we do that to both sides, we get x minus 1 is less than 3. And here I have 2, let's see. Well, yeah, this will work. So, okay, so now I can set up my two, a roundabout way of doing this is saying, well, when I take this out of the absolute value bars, I get x minus 1 is less than 3, how it was, but greater than negative 3. So that's a little trick there. But you should verify that this works. Like, why does this work? Well, it works because this thing is either going to be positive, we're either going to have x minus 1 is less than 3, or that thing is going to be negative. We're going to have that less than 3. And when we divide both sides by the negative, right here, it's going to flip the sign. And we're just left with x minus 1 greater than negative 3. Add 1 to both sides and get x is greater than negative 2. All right, so that's why this is going to work, okay? So anyway, side note, we're going to add 1 to both sides to get x is greater than negative 2, x is less than 4. What were we trying to do? We're trying to find the radius of convergence. Now, look at your notes, at your previous notes. What did I say about where the radius is in relation to the center? Right here. The interval of convergence will always be centered. Oh, wait, that's not the right one. Sorry, guys. Right here. The radius of convergence is the distance between the center and the endpoint. Okay? Either of the endpoints. So, going back to this problem here, our center, from the very beginning we saw what our center was. Our center is 1, just by this fact that we have x minus 1 in parentheses. The center is going to be 1, and so that means if we were to draw this out, here's my center at x equals 1. And then here's my endpoint, negative 2. And here's my endpoint, 4. And the question is, what is my radius? The distance from the center to either endpoint. What is that? How far is that? It's going to be 3, right? It's going to be 3. Cool. All right. So our radius is equal to 3. And what did I want to talk about here? I think we're just gonna stick with that there. Okay. All right. Let's move on. So we were just trying to find the radius. And let's do another example where we're not given a specific formula, where we actually have to find the formula here. So, how do we do it? How can we find a formula for this guy? I encourage you to pause the video and see if you can do it, if you can find a formula in terms of n for this. Okay, so here it is. We're going from n equals 1 to infinity, and I notice that the coefficients all correspond to the position or the n values. So on top, I have n times x to and the exponents also correspond to where they're at in the list, what the n values are. So this is going to be n times x to the n. And on the bottom, I have 2n plus 7. Okay, so that's my formula. And you should check that this works for n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. All right, so that's my formula there. Now we're going to go ahead and use our ratio test as per usual. So limit as n goes to infinity. Again, I'm plugging in n plus 1 anywhere I see an n to begin with. So I have n plus 1 times, maybe I'll just leave that as x to the n plus 1 divided by 2 times n plus 1 plus 7. And this is all going to be over the regular formula, which is just this. So it's all going to be over n times x to the n over 2n plus 7. Okay, let's clean it up. So clean it up, we're going to multiply by the reciprocal here to turn that complex fraction into something prettier. So we have n plus 1, x to the n plus 1. I'm going to do this distribution really quick. 2n plus 2 plus 7 is 2n plus 9. Okay, now multiply by the reciprocal. So times 2n plus 7 over n times x to the n. This is all in absolute value bars again. Let's see, what can I simplify here? Well, I can simplify, let's see. I can simplify the x's, really, and that's kind of it for now. I see this x to the n plus 1 divided by x to the n. So what I can do is just say this is simply n plus 1. X to the n plus 1 divided by x to the n is just going to be x. That's going to be times x times 2n plus 7 over 2n plus 9. All right. Now I want to bring that x out and keep it in absolute value bars, but since everything else is in terms of n, I can get rid of the absolute value bars there. So let's get that guy out of there. Get him out. Okay, then we have this, and then taking the absolute value bars away, we have n plus 1 times 2n plus 7, all divided by 2n plus 9. And we're like, okay, well, what's the limit here? Well, I'm going to simplify it, clean it up a little bit. I'm going to just first FOIL the top, or distributive property, if you're not into acronyms. So we have limit as n goes to infinity. Distributing up top, I get 2n squared, 7n, and 2n is 9n, and then 7. So that's just FOILing that out over 2n plus 9. Excellent. Okay. What I can do at this point, I mean, I can either do L'Hopital's rule, or I can divide by the highest power, which is what I'm going to do in this case. That's going to be n squared. So, and actually, I think I forgot something. Oh my goodness, I did. I forgot this n. You see that? Do you see what I missed here? I missed that n right up there. Oh, Sarah. Okay, here we go. So, I am so sorry. We have to distribute that n in there. So let's rewrite it. Okay, that looks a little bit better. So, I'm going to divide top and bottom by n squared. N goes to infinity of 2n squared plus 9n over n squared plus 7 over n squared over 2n squared over n squared plus 9n over n squared. Okay. All right, so these guys go away. These guys go away. This is just 9 over n. And same thing here. All right, so what happens when n goes to infinity? Well, we have 2 here, 2 here. This goes to 0, this goes to 0, this goes to 0. 2 over 2 is 1. So this limit is just equal to 1. All right. So this is our limit. And our question is, for which values of x does the power series converge according to the ratio test? Well, we have to set up our equation, right? So we have that in order for it to converge, the limit, which in our case is absolute value of x, better be less than 1. Better be less than 1. So doing our trick here, we can take that out, and it's going to be less than 1, greater than -1. And the whole point of this was to figure out what our radius of convergence was. And notice that in the very beginning of the problem, what is our center? What is our center? We have to look at that. Well, our center is 0, right? Because we have x minus 0 to the n. So our center is 0. And if we go back down here and examine this, this is equal to 0. And the question is, how far is 0 from either of the endpoints? What's the distance? Well, the distance is 1, right? So our radius is going to be 1. And maybe I shouldn't have even put that in a set. That's kind of weird that I did that. How about just like that? All right, our radius is going to be 1. Okay, so let's see. So again, another example here. I'm doing a lot of examples because I know this is a little tricky. So you guys should pause the video, see if you can do this one. But we're going to find the radius of convergence again. So I'm going to take the limit as I'm using the ratio test, the limit as n goes to infinity. Plugging in n plus 1 into my formula first, I get 4 to the n plus 1 times x minus 1 to the n plus 1, all divided by n plus 1. And then I'm skipping a step here, but remember you're supposed to divide by the formula you were originally given, but I'm just going to go straight into the multiplying by the reciprocal, because at this point in the video, I'm getting a little bit lazy. So we have that. And we're in absolute value bars. Don't forget about that. Now, I see some common bases where I can cancel things out or simplify them. I see this x minus 1 base on top and bottom. And I also see this 4 base on top and bottom. Now, the n and the n plus 1, I can't really do anything there. Okay? I can't do anything, I can't like cross out an n or anything. I can't do that. Not allowed. So let's simplify this. Well, 4 to the n plus 1 divided by 4 to the n is just going to be 4, right? So I just got 4 on top. And then x minus 1 to the n plus 1 minus n is going to just be x minus 1 on top. And then I have that times n over n plus 1. Okay, so I'm going to take the stuff that I can out of the absolute value, which is the n stuff. And then I'm going to bring the other 4 to x minus 1 outside. So what I have is 4 absolute value of x minus 1 on the outside, limit as n goes to infinity of n over n plus 1. And however you look at it, this is going to be 1. L'Hopital's rule, or divide top and bottom by the highest power. So what we get is 4 absolute value of x minus 1. And by the way, this was the ratio test, so this is our L. And our question is, for which values of x does the power series that we were considering, for what values of x does it converge? Well, we got to set up our inequality, because the ratio test says, hey, this thing's going to converge if it's less than 1. So let's do that. So we got 4 x minus 1 better be less than 1. I'm going to divide both sides by 4 to get that x minus 1 is less than 1/4. And then I'm going to do my little trick here, take this thing out the bars, leave that as less than 1/4, and then on the other side, it's going to be greater than negative 1/4. And finally, I'm going to add 1 to both sides. So I have x is less than 1 1/4, and x is greater than 3/4. So the radius is how far the center is from the endpoints. What was the center? Let's go back up. The center here is 1, right? X minus 1. So the center is going to be at 1. And the question is, how far is it from 1 to 1 1/4 or from 1 to 3/4? And the answer, of course, is 1/4. So my radius is 1/4. Okay, let's do an example here. So here it's asking for the interval of convergence. And what we're going to do with this problem, whenever your interval of whenever you're looking for the interval and it's not just 0 or infinity, negative infinity to positive infinity, you want to check the endpoints of your interval, because those endpoints occur when the limit using the ratio test equals 1. And remember that tells us you can't conclude anything there. So you have to kind of work around that. Let me show you what I mean. Okay, so let's see. We're on number 17. First things first is we're going to do our ratio test as per usual. So we're taking the limit as n goes to infinity. And I'm plugging in n plus 1 first into my formula. So we have negative 1 to the n plus 1, x minus 1 to the n plus 1, over 9 to the n plus 1, n plus 1 squared. Divided by, well, multiplied by the reciprocal. Again, I'm just like being a little bit lazy here, but hopefully you guys have seen enough examples to know what I'm doing. Multiplied by the reciprocal, so this is just our regular formula that we were given. Okay, and this is all in absolute value bars. So let's clean this up a little bit. Now, again, by the same logic that we used before, those negative ones are going to go away, essentially. And I now turn my attention to the x minus 1 base and this guy. When I simplify this, it's just going to become x minus 1 to the first. Okay, so we have x minus 1 to the first. Let's look at the 9. So we have 9 to the n over 9 to the n plus 1. Well, it's going to be 9 to the n minus n plus 1. So that's going to be 9 to the negative 1 when we do that distribution, which is 1 over 9. So that's going to be there. Then we have n squared over n plus 1 squared. All right, so far so good. Now I'm going to take out the n squared over n plus 1 and keeping x minus 1 in the absolute value bars. So, and I'll pull out the 1/9 as well. So I have 1/9 absolute value of x minus 1, the limit as n goes to infinity of n squared over n plus 1 squared. Cool. All right. So what is this going to be? Well, if I expand it out, I get n squared over n squared plus 2n plus 1 if I just FOIL the bottom. And if I divide top and bottom by the highest power, or you can use L'Hopital if you want, I get n squared over n squared over n squared over n squared plus 2n over n squared plus 1 over n squared, which is 1 over 1 plus 2 over n plus 1 over n squared. And obviously this is going to go to 1 because this goes to 0, this goes to 0, 1 over 1 is 1. Cool. So this goes to 1. And I'm left with 1/9 absolute value of x minus 1. This is my limit, L. And the question is, for which values of x does this thing converge? Now, why are we checking the endpoints again? Why are we going to end up checking the endpoints? Well, because instead of setting it up like this, so how we would usually set this up to find convergence is we would say, well, we would have a ninth, x minus 1 had better be less than 1. But if it equals 1, then we're going to get the endpoints. And remember, the equals 1 is the inconclusive case. Let me show you what I mean. So if we have a ninth, x minus 1 equals 1. Solving this, we get x, absolute value of x minus 1 equals 9. X minus 1 equals 9, and x minus 1 equals negative 9. And therefore, it's inconclusive when x equals 10 and when x equals negative 8. Inconclusive. So, ratio, this is where the ratio test is inconclusive. And that's why we're going to have to do some extra work here. So, now when we were just looking for the radius, we didn't have to do any of this because by definition, that radius is just the distance from the center of the power series to either endpoint. So we didn't have to do any of this, are we including these endpoints business? Okay. So, so let's go ahead and work this out. Again, we're going to have x minus 1 is less than 9. X minus 1 is less than 9, but greater than negative 9. So x is greater than negative 8 and less than 10. Okay? Now, what our question is because the ratio test was inconclusive at 10 and negative 8, our question is, do we leave it like this or do we put the little lines under it, right, for our answer? Because this time we're looking for the interval, right? We want to be careful here. So we need to check the endpoints. So let's do that. So check the endpoints. First of all, let's check x equals negative 8. When x equals negative 8, what we're going to do is we're going to just simply plug that in to our series here for x. So let me actually want to just write this down because I'm getting tired of, let's see, we have negative 1 to the n, x minus 1 to the n, over 9 to the n squared. All right, cool. So what we're going to do here is we're going to plug in our series. So our series was this, negative 1 to the n, x minus 1 to the n, over 9 to the n squared. If I plug in negative 8 in for x, what I end up getting is negative 1 to the n, negative 8 minus 1 to the n, over 9 to the n squared. Okay, negative 1 to the n, negative 9 to the n, 9n squared. Basically, this is alternating powers of 9, right? For n equals 1, that power of 9 is negative. For n equals 2, it's positive, and so forth and so forth. So I can write this as pulling a negative 1 to the n out to indicate that oscillation. So this is negative 1 to the n, negative 1 to the n, 9 to the n, over 9 to the n squared. These guys cancel. And this guy becomes negative 1 to the 2n, right? That's our exponent laws. When we have the same base and we're multiplying, we keep the base and add the exponents. So this is negative 1 to the 2n, which is always going to be negative or positive. Well, 2n is always going to be even, so this is always positive, right? So we have negative 1 to the 2n over n squared, which is the same thing as just 1, because this is always positive 1 for any n, over n squared. What do we know about this? We know that this converges. This is a p series, right? With p equals 2. We know that this converges. I don't know how I spelled converges there, but that was definitely not a correct spelling. We know that this converges because it's a p series with p equals 2. And since that converges, okay, yes, this converges for this particular value of x, which means we're going to include it in our interval. Okay, so we check that. Let's check 10. Let's check the endpoint 10. Let's do it. Let's do it. Let's check x equals 10. What's happening here? All right. Well, we're going to just plug in 10 for x. So we get -1 to the n over 9 to the n over 9 to the n squared. These cancel. And so my series becomes -1 n squared. Now, since we know that 1 over n squared converges, well, -1 to the n over n squared must also converge, because since it's alternating, we're only taking away numbers, right? So it's kind of like a comparison test in a way. So this, right? Because let me just make this clear. Let me just explain this a little bit more. Compare to 1 over n squared, which we know converges. Now 1 over n squared is just 1 where this guy, which we just found the alternating series of the same type, is going to be -1 plus 1/4 minus 1/9 plus ... So these things are nearly identical, except this one actually has less terms. We're like taking away more from the sum because of those negatives. So if this thing converges, then this thing also has to converge. So it also converges for x equals 10. So that's why we're going to add this guy. So this right here is our interval of convergence. So this is our answer. Just wanted to make that clear. This is our final answer. This is our interval of convergence. And by the way, what's the radius? Well, going back to the top, we know that the center is at 1, right? So this is at x equals 1, so the radius had better be a distance of 9, right? This is our radius, is 9. All right, guys. Well, I hope you guys learned some cool stuff about power series in this lecture. Thanks for watching. I'll see you guys next week.